Hello, everybody. Welcome to our last class of the semester. Okay, all we have really missing today is just solving a couple of exercises from our list of section 6, and this is what I will do now. Other than that, we also have your homework pending, and the solution of that exercise, which is actually not very difficult, and you are all pretty much getting it done, I will upload it to the virtual campus just on its own as a PDF file. Okay, so today we're just going to work on the exercises on section 6 because I don't really want to, I want to focus your attention on this section and not just go back to different contents. Okay, so the first one we have to solve is exercise number 7. What do we have here? In exercise number 7, there is a very thin cylindrical shell of radius r, capital R, with is charged with a surface charge density sigma. Okay, since this is a conducting shell, obviously the charge is going to be distributed homogeneously over the whole surface of the system. Okay, so first of all, they say find the electric field throughout the whole space. This is not going to be difficult because it's an electrostatics problem and we'll solve it fairly easily. And then next, the shell, and this is the new part, starts to rotate, spin around its axis. Then this means we're going to have all of this distribution of charge spinning at a constant angular speed, and therefore that will be like a current. And as a matter of fact, it's just not any current, it's going to be like a solenoid because let's say the filaments of current are actually flowing in circles. Okay, so the thing is that this angular velocity is not going to be constant, but it's going to be increasing linearly with time. So it's an accelerated motion, right? So omega is going to be alpha naught equal t. So they say find the electric and magnetic fields in all of space along with the Poynting vector in this case, and check the Poynting's theorem on a cylindrical volume of radius slightly smaller than capital R. So this is on the inner surface on my cylinder. This will be relevant whenever you have to check Poynting's theorem. Really, you need to realize what is the surface of interest. So here is just right inside the cylinder, okay? Right. So anyway, for the first part of the problem, it's really an electrostatics problem. You have to realize this is a problem of cylindrical symmetry as usual. So all of our electrostatic and D displacement fields are going to be parallel to the radial direction, and then we will apply the Gauss law to find the fields as we used to, for example, for D. Okay, so as you know how to do this, the flux of D across any closed surface is going to be equal to the free charge inside the surface, and in this particular case, I'm going to take a Gaussian surface, which is like a cylinder concentric with the axis of our cylinder, and therefore its flux, the flux of D will be D times the surface of the cylinder. This is 2 pi RL equal to the charge inside. Okay, so when my surface of interest, the Gaussian surface, has a radius smaller than capital R, there is no charge at all inside that surface, and therefore the fields are 0. No big deal. I'm actually looking at the hole inside the cylinder, no charge there. And when the radius is larger than capital R, then the total charge I'm looking at is going to be the whole charge on the cylinder. This is going to be pretty much sigma times the surface. And if you do that, it's not difficult to realize after getting all this factor 2 pi RL all the way dividing the total charge, that the D displacement vector equals sigma capital R over R UR, and therefore the electric field is going to be D over epsilon naught. This is just electrostatics, should be quite easy. So this is the electrostatic fields. And by the way, note that this is the electrostatic field that is always going to be present before and after the spinning starts. Okay? Before the spinning starts, the charge is static. After the spinning starts, the charge is rotating. However, since the charge distribution is homogeneous, the picture at every single moment of time, if you think about it as like single photos, single shoots, is the same. So the electrostatic field is always there. It doesn't change over time. Okay? All right. So that is the first part of the problem. That was the easy one. Now we have to find the electric and magnetic fields and the Poynting vector through the whole space. Now, know that now that the shell is rotating, you have to realize that if the angular velocity increases linearly with time, the problem is equivalent to having a solenoid where the intensity flowing on the loops, on the turns, increases linearly with time as well. All right. The internal field in the solenoid we will be able to calculate it as usual, just for any solenoid, just that it will increase with time, just like the intensity. It will be uniform and homogeneous through the whole internal volume of the cylinder, but it will increase. All right. Now, what is the intensity or the equivalent intensity we think about this system being equivalent to a solenoid? We'll just like look at whatever one point on the surface and start counting for a whole turn of the cylinder, which takes one period, right, capital T, how much charge goes through my point of measurement. In other words, the intensity will be the total charge over T, the period. The total charge for a turn is going to be sigma times the surface, the lateral surface of the cylinder, that's total charge. The time it takes to take a turn is a period, all right? Now, what is the period? Well, omega over 2 pi. The only thing is that omega, the angular speed, will depend on time. But other than that, this is no big deal. So I can actually arrive to the finding that this azimuthal intensity going, okay, around the whole cylinder is going to be sigma, the charge density, R, capital R is the radius, L, height of the cylinder, alpha naught T, okay? Now that I know that, I can actually calculate the magnetic field inside my cylinder, all right? Since I know the intensity going laterally around the whole surface of the cylinder, the surface current density equivalent to this movement will be intensity over the length perpendicular to the transport when I'm evaluating the current, okay? This length is actually L, right? So the surface charge density will be I over L, and this is pretty much going to be free current, all of it is going to be azimuthal, and it's going to be equal to sigma R alpha naught T, because these two L's are the same and they go away, okay? Now that I know the free current flowing, I can get H. I can do it just like if it was a solenoid, and if you don't remember or you don't realize that this is like a solenoid, you can also do it using the boundary conditions. Let's do it like that, just for the sake of having more ways of doing things. The boundary condition for H on a given, when we go through any particular interface, and in particular, let's go from the inside of the cylinder all the way out to the outside of the cylinder and consider the cylinder so thin that it's just basically a surface with this free charge flowing on it, okay? So the parallel component of H, parallel to the interface, right? In other words, parallel to Z, which is the direction of the interface, for example, along this line right there, this height, will be equal, we can calculate it as the free current cross the normal vector, but the normal vector is the unit radial vector in this case, which point outwards, in other words, perpendicular to the interface between 1 and 2, inside and outside the cylinder. So Kf is alpha naught T times capital R sigma, okay? The free current goes like azimuthal, U phi, the normal vector is UR. This cross product can be easily seen to be like minus UZ, the Z, the cylindrical Z, the axis of the cylinder, right? So we also have to take into account that outside my current distribution, just because of the symmetry of the problem, just like a solenoid, the field is 0, okay? So in other words, minus H1 parallel, in other words, the field parallel to the Z-axis is going to be equal to minus sigma R alpha naught T UZ. So the field inside the cylinder is going to be H field sigma R alpha naught T, and it's going to be vertical. All right? The currents go like counterclockwise. So with the right hand rule, well, the field has to go vertical. Surprise, surprise. Okay? So that is the magnetic field inside the tube, and if you do it using the comparison to a solenoid, you should arrive to the same result. Anyway, therefore, the magnetic field B, since the inside of the cylinder is empty, right, will be just mu naught H, and therefore this is the magnetic field inside the cylinder, mu naught sigma R alpha naught T times UZ, and 0 outside. The interesting thing here is, of course, it's a magnetic field that depends on time. Okay? This means that there's going to be an induced Faraday field, a non-conservative field across my system, just because, of course, my magnetic field is variable. Okay? So at the end of the day, if they are asking about the total electric field in the system, it's going to be the electrostatic contribution plus this non-conservative contribution, which we have to find. Let's do it. Well, we can use the Faraday Law and then sort of calculate the circulation of the non-conservative induced electric field along any curve like this closed circle, which is perpendicular. Okay, it's contained in a plane perpendicular to the cylinder axis, right? Because the symmetry of the field has to be azimuthal, just as usual. And then we have already done this for similar systems. Inside the cylinder, the field times 2 pi r, which would be the contribution to the line integral of the non-conservative field, has to be equal to minus the derivative of the flux of the magnetic field. But if the curve C that I'm calculating on has a radius smaller than capital R, then the flux of the field is B times pi r squared, right? I put that in here, and then I do the time derivative because B depends linearly with time, and this is what I obtain. So I can get inside the cylinder, the non-conservative field is all of this over 2 pi r, okay? This is the thing, and it's gonna go azimuthal, so I can put the U phi in there. See that this field actually circulates just in the opposite sense because the magnetic field is increasing with time, the primary field, so the induced Faraday field would be such that it would induce currents if it could. That would kind of try to generate a secondary field opposing the increase of the primary field, and therefore they will have to go clockwise. This is why this comes like minus U phi at the end of the day, okay? Now, inside the cylinder, since we are in a region where there is no electrostatic field, the total field will be just this Faraday field. Remember, I am inside the charge distribution, so if there is any Gauss law to be applied in there, there is no inner free charge. Well, then no field. Just go back to the field, the electrostatic field that we found in the previous slide. Now, outside the cylinder, for regions where R is larger than capital R, the radius of the cylinder, in other words, if this C curve was larger, okay, than the cylinder, then I can apply the same Faraday law. The only thing is that in this case, the flux of the magnetic field is contained just on the surface of radius capital R, okay, because there is no field outside. So in this particular case, I would arrive to the realization that the non-conservative electric field has slightly different shape right there, goes like 1 over R, surprise, surprise, just like all of the problems we have done so far. And in this case, outside, there is an electrostatic field. So the total electric field is going to be the sum of the electrostatic field, this one, which is radial, plus the non-conservative field that is azimuthal. So it's going to have it's going to be both radial and azimuthal. So it's just like going to rotate around the solenoid, but at every point, the field is not going to be tangent to the circle, but it's going to be deviated slightly towards the outside because the charge is positive. Sigma is positive. Okay, so it has there right there 2 contributions, and that will be the total electric field outside. Okay, just see that. My total field inside is just the non-conservative region. Sorry, contribution outside is both the conservative and the non-conservative contributions together. All right then. How about then the Poynting vector? Well, I can calculate E cross H. In other words, 1 over mu naught E cross B. I have E, I have B, so this would be the value of the Poynting vector, right? For example, outside, I have used here the magnetic field, the electric field outside because, no, actually, sorry, this is inside right there. Well, as a matter of fact, I am going to calculate S right at R equal capital R. And these fields are the non-conservative field is actually continuous, if you think about it. You put it a capital R here or a capital R there you get the same result, so it's not really very important. So this is going to be the electric field right at a distance of r equals capital R, but I'm going to be interested in just slightly below capital R, so just on the inner part of capital R, very, very close to the inner surface of my cylinder, okay? So that is the value of the electric field there, and then the magnetic field, of course, is not 0, but it's all of this mu naught sigma r capital. Anyhow, you substitute those and you get this. The Poynting vector actually is going to go like minus ur. In other words, there is some power flowing inwards through the surface. We'll talk about this in a moment. Let's check about then the Poynting theorem on the surface, just on the inner surface of the cylinder where the radius is close to capital R, but slightly smaller. Then we have to check that all of those terms just hold on together. First of all, the power, the joule power is 0. Why? Just think about it. This term is the integral of the current dot the electric field. But right inside the cylinder, we are in empty space. Inside but empty. There are no currents there. Okay, so if there is no conduction current on the surface of interest, well, there is no dissipated power because there is no joule heating. Nobody's flowing with any sort of friction there. So that term goes to 0. Now we have to calculate then, this term is not interesting, then we have to get the electromagnetic energy. The electromagnetic energy is going to be the electromagnetic power, which is the derivative of the energy with respect to time, is going to be the contribution of two terms, the electric energy plus the magnetic energy. Now, the electric field E does not depend on time. It depends on the distance, if anything, but not on time. So the derivative of the electric energy with respect to time is 0 because the electric field is constant. The energy contained in the field stays the same all the time. So the derivative, the electromagnetic power is only going to come from, let's say, magnetic power. In other words, the variation with respect to time of the magnetic fields and the energy stored in the magnetic field. That's the one we have to look at. Now, this magnetic energy can be calculated as 1/2 of the integral of B dot H. And now if we put B and H in there, we already had the fields before, we arrive into this integral, right? And, well, it's not a very difficult one because I have a volume integral of things that are basically uniform in space. They don't depend on the coordinates. So what I get is 1/2 of all of those constants times the volume, okay? And then the result is right there, and it depends on time. Yes, it does, like t squared. So then we just do the derivative over time, and then we actually get to this result, and this is going to be the net variation of electromagnetic power. Okay, the term I was looking for to put into the Poynting's theorem. Okay, I'm going fast because this is not difficult so far, is it? Anyhow, finally, we also have to check the second term, actually the third term. We already have the mechanical power is 0, the electromagnetic power, we have it, and now let's check the flux of the Poynting vector on the surface of interest. There are two capital R's there. I'll fix that on the slides because obviously one of them, there are just one too many R's right there, my bad. But anyway, the flux of the Poynting vector on the inner surface of the cylinder, just inside, in other words, on the empty surface that sort of touches the cylinder inside, okay, is going to be a sum of the lateral, the flux of the Poynting vector through the lateral surface plus the flux of the Poynting vector through the leads. However, the Poynting vector is radial, so the leads do not contribute, to the flux because S is radial. ds would be like UZ or like minus UC for the bottom lead. The dot product is 0. So all I care about is the contribution through the lateral surface, okay? And over there, ds goes like UR, so the flux is pretty much just the modulus of S at capital R times ds, and then it's not difficult to see that this is just the modulus of the Poynting vector at capital R times the lateral surface, which is 2 pi capital R times L, the height of the cylinder, and this is what we get. So now we have the flux, we have the electromagnetic power. Does the theorem hold? Well, first of all, first term, electromagnetic power. That's what we got in the previous slide. Second term, flux of the Poynting vector, this one, right here. And I am missing a pi. Well, there is one pi there. I'm missing a pi factor in there, am I not? We have the T, we have the L, we have the R4, we have the alpha square, the mu naught, we have the sigma square. Where is my pi in the electromagnetic power? Let me go back for a moment because I've missed it somewhere. Oh, well, of course, in this dV. Okay, the volume of the cylinder, right there, is going to be pi r squared times the height. And this is an r squared comes from here, the height comes from there, and there is a pi missing. I'm going to fix that right now, and I will share in a moment. That's where we were. First term, second term. Now that looks all right. Okay? So indeed, the Poynting theorem holds, as it should. And I would say that all of the flux of energy coming into the system is actually getting invested into changing the magnetic field there. There is no heating inside the tube because there is no current, okay? So all of the energy that we are putting into this increasing field is actually being stored in the increasing field. All right, that would be another one. And now we have problem number 6, which is very long and endless, okay? But pretty much summarizes everything. So number 6, exercise number 6, says that a long and narrow solenoid with a radius A and n turns per unit length, okay, it's like right this one here, has a current flowing through it initially, I naught, constant, but then we turn off the external power supply and this current starts decreasing and until it vanishes, it goes to 0, right? So this transient, this time while the current is decreasing, the current actually, the dependence with time is going to be like I naught initial value minus KT. So this is a linear dependence with time, okay? That is the thing. Now, outside the solenoid and coaxial with it, we have put a conductive metallic tube, that's a cylinder, of radii B and C, such that obviously B is the inner radius of the cylinder and C is the outer radius of the cylinder. This material is conducting, has conductivity sigma, a permittivity equal to epsilon 0, just like all metals, and a permeability equal to mu naught. So there are no magnetic material effects to be having to account here. Okay? So during the time it takes to cancel the current intensity, so this whole transient process where the intensity goes from I naught all the way down to 0 in a linear fashion with time, calculate. First, the currents induced and the power dissipated in the tube. Just keep in mind, there is a magnetic field in the tube that is decreasing because the intensity is decreasing. Therefore, there's going to be a Faraday field, which is located everywhere, both inside the solenoid and also outside. This field, just because of the length law, wants to oppose the decrease of the primary magnetic field. In other words, it would induce currents, and it will in the metallic shell, that rotate in the same direction than the primary intensity. If this one goes counterclockwise, so will the induced currents. So they produce a secondary magnetic field, an induced field, that points upwards and tries to compensate the decrease of this upward pointing magnetic field, the primary one. Okay? So there will be an azimuthal electric field induced that goes just like counterclockwise according to the right-hand rule, just like the primary currents. Just calculate those currents and the power dissipated by them in the tube. Second, these currents obviously are going to induce this secondary field, this induced magnetic field. Calculate it. We'll do that. Third, calculate the magnetic energy stored per unit length in the solenoid. Now we're going to have both an induced field and the primary field. What is the energy stored in those? Okay, which is obviously going to change over time. Then the flux per unit length of the Poynting vector through the tube. Okay, and you can already imagine where this is going to at some point. It's going to say check the Poynting theorem. Okay, we will. Then E, the energy balance by checking Poynting's theorem, surprise, surprise. And finally, and this is the last thing, now imagine that instead of the conducting tube, so we remove the tube, we had a metallic rod of length 2a, a is the radius of the solenoid, which is placed symmetrically at a distance 2a from the solenoid. What this means is if the solenoid is vertical, we put the rod like that, perpendicular to the solenoid, okay, and at a distance 2a. Find the potential difference between the ends of the rod. Those are going to see a non-conservative electric field, remember? So there will be a potential difference that we will calculate. All right, let's go one by one then. First of all, the strategy here obviously is to realize that there is a time-varying intensity and therefore there is a time-varying magnetic field, which decreases but it points upwards. So a non-conservative azimuthal electric field is going to be induced, like we said, and it will appear everywhere, right, including the region of the cylinder, the conducting cylinder outside. So this problem has cylindrical symmetry and this non-conservative field will be azimuthal. And it will, like we just said, rotate counterclockwise, just like the primary current that is decreasing. And I will say that again, it will be, we have to see that it will go counterclockwise like that because this non-conservative field in the metal, in the cylindric metal, wants to give rise to a density of currents that generate a secondary magnetic field, a secondary induced field that wants to point upwards in order to try to counteract the primary effect, which is a decrease of a 0.1 of the initial field, okay? Right, so let's calculate all of it, all right? First of all, the induced currents on the outer cylinder. Well, for this, we need to calculate the non-conservative Faraday field, and then we'll use the Ohm's law to calculate induced currents because current equals sigma, the conductivity, which we know, times electric field. Well, let's apply the Faraday law. Means we have to calculate both terms, the line circulation of the electric field and the flux derivative with time. We don't know the value of the non-conservative field, but we know it's azimuthal. So if we actually calculate this line integral along a circle like this C here, right, of radius larger than a, whatever, and therefore dl is also azimuthal, of course, this integral becomes modulus of one thing times the modulus of the other one. The modulus of the non-conservative field is not known, but is constant on the whole curve C, the circle of constant radius, goes out of the integral, and then I have the integral of dl, which is just the length of the circle. That's the first term. How about the second term? The magnetic flux is B times ds across the surface, but basically this is just going to be B is homogeneous, goes out of the integral if you want to, and then S is the surface filled by the magnetic field, which is the section of the solenoid. Okay, so the field of the solenoid is mu naught Ni, but this is the intensity that changes with time. The area of the solenoid is pi a squared, so this is the flux, and its derivative with respect to time will be just that. Now we make this equal to that, and we get the non-conservative electric field for regions outside the solenoid of radius A. And this is what we get. A field that, surprise, surprise, just like every single time we're calculating non-conservative Faraday fields outside solenoids, it goes like 1 over r. And it's azimuthal, and it goes just like the primary currents. Good. This is good for the region outside the solenoid. And then, of course, the density of induced currents will be just the conductivity times the field. Okay? So this is it. Interestingly, realize just that this current depends with 1 over r. The thickness of the cylinder is finite. The inner radius is B, the outer radius is C. So there will be a different amount of current flowing near B than near C. Okay? The current decreases with 1 over r as well. So it's not homogeneous inside the cylinder. There is a dependence on r, the distance to the axis. And we'll need to have that into account a bit later. Hold on a minute. All right, sorry, thank you. Now, let's keep going with this endless problem. Now, say next thing they say, all right, there is a conduction current flowing on the outer metallic cylinder, what is the power dissipated by it, the Joule heating. All right, let's do it. The power dissipated will be just the integral of the non-conservative electric field, which is all the field we have is that one, times the induced current that we just calculated. If you want to use the Ohm's law again, it's pretty much the same thing. Since J equals sigma E, well, just do the integral of sigma E squared over the volume. Now this is the sigma electric field that we just calculated. We have to integrate this thing over the radius, right? R, the radial coordinate, because it depends on R. The differential volume for a cylinder, just as usual, will be a small cylinder of thickness dr. So this lateral surface times its thickness. This is the dV, and we are integrating R. Oh, from A to B? No, this is wrong. It's from B to C. We just fixed it. There we go, from B to C. That's the volume of the cylinder, right? So well, this is an integral that is going to end up going like 1 over R, because here we have 1 over R squared, and then we have an R here. So the result is quite obvious. This is what you get. All of these constants times the logarithm of C over B. That is the dissipated power within the cylinder due to the conduction current circulating counterclockwise. Okay? All right, then. Next thing they say, oh, well, we have all this current circulating in the outer cylinder. They will generate a magnetic field inside. Yes, of course they will. Let's calculate it. These currents in green here will kind of produce a magnetic field inside, and this actual outer distribution of currents is sort of like a solenoid, so it will generate a field inside that is homogeneous. Okay, and like we said, this field is going to point up along the z-axis, just like the primary field that is decreasing, and this guy wants to say, no, do not decrease, I will help you. Okay, so it points upwards. So in order to calculate it, what we must take into account, and now we have to take it into account, is that within the thickness of the metallic cylinder outside, the distribution of current is not homogeneous along the radial direction. It decreases with R. So we have to do an integration there. And in order to calculate the total magnetic field inside, I'm going to think of this distribution of currents as a superposition of cylinders. Each one of them is like a solenoid. So if I just cut the system across the cross-section and I just look at it right there, this is what it looks like. Here is the inner solenoid I don't care about. So this is radius A. Now this is the cut of the outer cylinder, radius B, radius C. And the currents are going like that. So over here, I will assume that they're coming out of the plane of the paper, and here they go in, right? And then I'm going to take a small cut, just like a surface, all right? Just like a lateral surface of a cylinder of small thickness dr, and I will think that's like a solenoid, right there. So what I have to see is the small contribution to the magnetic field of this small cylinder of thickness dr, right? What magnetic field does it generate inside? This small magnetic field will be mu naught times the current K, surface current K flowing on the surface. And, this K actually goes like U phi. No, sorry, I mean, this is good. These are always wrong. I'll fix that in the slides. But actually, this is what you should get. Mu naught times the current, and it will go like UC because it's vertical. The field is vertical and it points upwards. And the modulus of decay is intensity over length perpendicular to the transport. The field lines, the intensity lines are going inwards, for example, there, and the length perpendicular to the transport is just the whole length of the solenoid. We have to want to know the whole intensity there. Okay. So the whole length is L, capital L. The intensity going across this orange surface is going to be J, the induced current density that we just calculated, times the surface perpendicular to the transport, the section, which is the surface of this orange rectangle, which tries to mimic the section of a really, really thin cylinder, right? And this is basically going to have a surface of L. This is the height times the width, dr. So at the end of the day, the differential, let's say, surface current is J times dr. Let's put that right in here and calculate the whole magnetic field in there, consisting on the superposition of the small magnetic field generated by every small cylinder that we can think constitute my thick metallic cylinder of inner radius B, outer radius C, so just a small cylinder of radius B, and then a bit more, all of those together, all the way up to C. So if I do the integral from B to C, all of those fields, it's pretty much a fairly easy integral. The whole magnetic field in there comes out to be mu naught times the current distribution, which I don't have right here, but it was in the previous slide. Let me go back for a moment. I'm not doing things too fast. There. Okay, goes like 1 over R. So I'm going to have lots of constants, but again, at the end of the day, the integral of this thing is going to be a logarithm of C over B. And this goes like UC, okay? So this is the induced magnetic field, induced by the induced currents, induced by the non-conservative Faraday field. Oh, well, there's an animation missing there. Sorry about that. Let's just look at the upper part of this slide. So now we can calculate the magnetic energy stored in the whole solenoid. For the same, we must keep in mind that the total field in the solenoid will be the superposition of both the primary and the secondary fields. The primary is the one due to the external current that is decreasing over time linearly, and the secondary one is the one induced by the currents that we just calculated. So the total magnetic field inside that we need to take into account to get the density of magnetic energy, which will be B squared over 2 mu naught. There is pretty much emptiness here, okay? There is no magnetic material, so that's a good way to put it, will be the superposition of the magnetic field of the solenoid, the primary one in the first place, plus the induced fields. These are both of those squared, okay? Now we integrate to get the whole volume, the whole energy in the whole volume of the solenoid, which will be with the integral of the density times dV. Since this is actually not depending on any spatial coordinate, the density is uniformly distributed over the whole volume. In other words, the total magnetic energy is just the density times the volume, and they just calculate the magnetic energy stored per unit length. So total energy over total length, just right there, will be the magnetic energy times volume of the solenoid, because they ask about calculating the solenoid, surface pi a squared times total length over length. In other words, all of this, which is the density of magnetic energy times pi a squared. Okay? Right there. Now, next thing, calculate the flux per unit length of the Poynting vector through the cylinder surface. All right, let's do it. There are two surfaces here, by the way, the inner and the outer surface, R equal B and R equal C. Let's do both. At R equal B, this is the inner surface, the Poynting vector is going to be the electric field cross H. In other words, the electric field cross B over mu naught. Now, outside, the only field we have is the field due to the induced currents. Okay? So we have to put in there the magnetic field at B. That's what we want to calculate. And since we have the field, all you need to do is substitute and do the cross product, and it goes like UR. This is the final result. This is the Poynting vector at the inner surface of the cylinder. It points radially inwards towards the axis of the solenoid. How about C? Well, the Poynting vector at the outer surface, and this is interesting, will be the induced field, electric field at C, which is finite, times H at C. But there is no magnetic field at C. Okay? Because the induced currents are inside the volume sort of contained by a cylinder of radius C. In other words, we are sort of thinking of like the surface of a solenoid, and there is no field at the outer surface of a solenoid because we are already sort of outside. Okay? So H at C is 0, and therefore the Poynting vector on the outer surface of the cylinder is 0. And this is an interesting result, because if the Poynting vector is 0 on the outer system, on the outer surface of my system, this means that there is going to be no flux of energy going in and out through the surface. So whatever is happening regarding the energy, whatever you're hitting, power being put into whatever mechanical work, blah, blah, anything you want to think about is always going to be confined to inside the cylinder and the solenoid, but nothing is flowing in and out, in or out. No energy flux. And we'll come back to this a bit later. But then let's calculate the flux through the inner cylinder surface, the flux of the Poynting vector. Obviously, there is no point on doing it at R equals C as we just discussed, but we'll do it at P, R equal B, and then per unit length. So this is the flux at R equal B per unit length. This is what I need to calculate. Just keep into account that for the inner surface of the cylinder, the normal vector is going to be minus UR if we want to point inwards, because the ds, the surface vector over there, points towards the axis inside. Okay, so we have to calculate pretty much the integral of S dot UR with a minus in front of it, and then we know the Poynting vector already can go out of the integral, so I just get to the result. Here is the flux. If you put the Poynting vector that we just calculated in there, you can arrive into this expression. And since C is larger than B, this whole term is negative, okay? We'll talk about that a bit later. But it basically means that energy flows from the solenoid into the tube, warming up the conductor. Due to the Joule effect, surprise, surprise, there is energy coming from the primary magnetic field. This is the Faraday electric field that is inducing currents. So there is mechanical work, if you want, to be input into the external charge in the cylinder, starts moving, inducing currents and heating up the system. And this energy is coming, let's say the power supply here that forces these induced currents to circulate is the solenoid with its varying magnetic field. Okay, so this is what this negative sign means. All right then, so now let's calculate now the energy balance by checking the Poynting's theorem on the conducting cylinder on this surface, okay? We have to check all of these terms individually. Actually, we have already calculated a number of them. See, this is the mechanical power, J dot E, and then this is the variation of the electromagnetic energy, fine, and this is the flux of the Poynting vector. We have already calculated almost all of those. The only one that we have not looked at so far are the currents and the field in the cylinder. So that would be the first term if you want to. But there is an interesting thing there to be noted, and it's that the non-conservative field and the induced magnetic field, both of them are constant in time, at least as long as the intensity is decreasing linearly during this transient period. All right? So if those are constant, the electromagnetic energy contained in those two fields is not going to change with time either. In other words, the electrostatic, no, it's not electrostatic, but electric energy derivative with time is zero because the field is constant. The magnetic energy contained in the magnetic field is constant because the field is constant, and the derivatives with respect to time are zero in both cases. So the electromagnetic power change, I mean that the change in the magnetic energy, in other words, the electromagnetic power is zero. Now, that term that was the one we were missing is zero. The other two, the Joule heating, we have already calculated. The flux of the Poynting vector at the inner surface of the cylinder, we have already calculated it. Does the theorem, the Poynting's theorem, hold? Let's see. Power, this term, equals minus the derivative of the electromagnetic energy, which is zero, forget about it, minus this flux. And it won't take too much work for you to realize that this term and that term actually are the same. So the Poynting's theorem actually holds. And like we said, all of the power here is dissipated in the cylinder in the form of Joule heating. Nothing goes out through the outer surface. Okay? Finally, now let's remove the outer cylinder. Let's think of the same problem. We still have the solenoid with this intensity that is decreasing over time from an initial value I0 all the way down to 0, linearly. All of that is the same, but just remove the cylinder, and instead, let's place this metallic rod of length 2a in a plane that is perpendicular to the axis of the solenoid, so that this is placed symmetrically, this is at the middle of the solenoid, and at the distance 2a from the center of the solenoid. Question is, calculate the voltage difference between the extremes of the rod. The extremes, if there is any. And the thing is, yes, there will be some voltage difference between those two, because the rod will feel the effects of that non-conservative Faraday field. The field is still there because this magnetic field, the primary field, is still decreasing. And there will be a different non-conservative electric field at one extreme of the rod than the other extreme of the rod, and that will give rise to a voltage a difference of potential, a voltage change. And you say, wait a minute, the ends of the rod are at the same distance from the center. So the modulus of the electric field will be the same, right? The modulus, yes, but not the direction. As a matter of fact, remember that the non-conservative electric field is actually tangent to the circle. So if we actually look at the system from the top, what do we see? Here is the solenoid. This is the azimuthal non-conservative field. This is my rod. The extremes of the rod will see two non-conservative fields, non-conservative field number 1 here, non-conservative field number 2 there. They will have the same modulus, but not the same direction. And you know, for a vector to be, the same, it has to have the same modulus, same direction, same sense. This is not happening here. Okay, so there will be a voltage difference between those two. And in order to calculate it, we have to go from one extreme to the other extreme, number 2, and do the integral of the non-conservative electric field there. dl in this case, obviously, is going to be a piece of rod. And if I look at things from the top, and my z-axis was in the axis of the solenoid, this horizontal axis right there is my y-axis, and the axis coming out of the plane of the drawing will be the x-axis, just like that. All right? So dl is pretty much dx times ux. Okay? So the product of the non-conservative field dot product times dl is going to be just the x component, the projection of the sums of the x components of this field. That will be just projecting things along the direction of this blue line that represents the rod. And if I call alpha this angle, this is the same thing, just because these angles are complementary and you look at them, they are rotated a sort of 90 degrees. The horizontal component of this green vector, I can get it pretty much like that with the sign of alpha right there. Okay? I'm talking about this one, and then I can, if I call this coordinate x and this one is y, I can talk about the r coordinate is a modulus of x squared plus y squared. The sign of alpha is y over r right there. So that is the x component of the electric field. I'm going to put that in here, and I'm going to integrate from 1 to 2, which, by the way, is the point where x equals minus a all the way up to x equals plus a. And during this whole trajectory, y is constant, equal to 2a. Just look at this, the geometry. Y is the distance, right? That one is the same, always is 2a. So I'm going to put that in the y square, 2a, 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 everywhere, and I'm going to integrate my x dimension from minus a to a. And if you do that, and if I did it right, which I might not have, but you check it and let me know if it's not correct so I can get the right the right version of the solution, but it's not going to be very far off. Okay, what you get here is an integral that is just like an arcotangent. Okay, and after you do the whole calculation, you arrive into a voltage difference between the ends of the rod that looks like this. Okay, and like I said, maybe I got the integral wrong. I hope I didn't. But the important thing is that this is a negative number, meaning the voltage at 2 is lower than the voltage at 1. Does this at least make physical sense? Just to see whether this is more or less right. In case you were in the exam and you had something like this, well, let's look at it. The electric field, the non-conservative field, from here to there points, the net component points downwards. And electric fields, no matter whether they are conservative or whatever, they always point to regions of lower potential. In other words, it's not crazy to think that the potential here is smaller than over there. Final minus initial negative, okay? So at least that part is probably okay, right? All right then. So this is the end of problem number 6, which is a very long problem, but this is what we have. And with this, our electromagnetism semester is over. There is just one more thing that we are missing, and is the solution of the homework. This is, remember, the problem that we had left from the previous section 5. Now, I am actually recording this class on Wednesday, the January 20th in the evening, and the deadline for turning in the homework is not is actually tonight at midnight, right? So I'm not going to solve this exercise right now, but it's not a very difficult one, so I will upload the solution to the virtual campus so you can check it on your own. And if you have any questions, let me know, okay? Well then, with this, please let me know you have questions on the things we said. I went a little bit fast over the math, but you see the math is not difficult with all these things about pointing and friends, right? It's more about understanding the physics, like what are the flows of energy going in and going out, and whether the final results at least make some sense from the physical point of view. So I hope that went well. And like I said, let me know if you have any questions or if you see any typos or any errors on the slides so I can fix them. And with that, we are done. And I will see you at the exam, which I'm sure you will do very well. Okay? Well then, take care and talk soon.